With us tonight is Dr. Bob Pappalardo. So let's welcome Bob.
Thank you. It's a pleasure to be here.
And it's such a pleasure to have you here. We've known each other for an awfully long time, and we've talked about having you come for an awfully long time. So it's finally happened.
Great to finally be here.
And I'm really happy you're here.
What fun. And then I get to talk with you about one of the most exciting places in the solar system, Jupiter's moon, Europa. And why is it so exciting? Because it's like really no other object out there, and because we believe that there's a subsurface globe-girdling ocean beneath Europa. We'll see Europa a little bit, and then we'll also talk about the mission to get there that NASA is finally doing after many years of working to get this mission started. We even are premiering here our new beautiful model of the Europa Clipper spacecraft, which we'll talk about in a little bit. So Europa is one of the four big moons of Jupiter, a lot of little ones, but the four Galilean satellites, Io, Europa, Ganymede, and Callisto. Ganymede and Callisto are kind of half ice and half rock. Io, as you know, is a rocky object and the solar system's most volcanically active body. Europa is kind of in between. It has a density that tells us it's actually mostly rock, but there's a skin of H2O, some of it frozen on the outside, and we're pretty sure some of it liquid on the inside. So there's Europa closer up. You know, most moons you look at and they're covered with craters. Europa has very few craters. One of them you can see in the bottom there, and it's called Pwyll in the bottom left of the image up there, or Puch if you're Welsh. Can't quite get that right. The bright areas of Europa, especially near the poles in that global image, are covered with ridged plains. So places where ridges and grooves are cutting across the surface. We don't really understand how these features form, though they're the most common feature on Europa's surface. It might be ice sort of oozing up through fractures, pushing up the surface above. There are these chaotic terrains. Those darker areas are aptly named chaos, places where the surface seems to have broken apart, probably because of heating from below. And when we see smaller spots, we call them lenticulae. That's Latin for freckles. And we think they have to do with churning of the ice beneath, as we'll see. This is what we think Europa's innards look like. And we know that from gravity measurements that tell us that Europa's has probably an iron core down there and a rocky mantle, and then about 100 kilometers worth of H2O. And we think about 20 kilometers of that is ice, and that would leave the remaining 80 kilometers or so for water. Now, we're not sure. You know, these are estimates based on, well, gravity data for the interior structure there, but then geologic features and arguments from thermal models as far as how thick the ice is. So we really don't know very well, and that's part of why we're going there, to understand that. Europa's ocean, the volume of it, is probably on the order of twice that of all the Earth's oceans combined. You can see little balls of water there that represent piling up all of Earth's oceans in one volume. Europa is probably about twice that. Now, how do we know there's an ocean down there? I'm a geologist, so I like to think we know it from geology. We have indirect evidence from geology that we'll see. But the most direct evidence is from the magnetic field in the vicinity of Europa. So Europa is orbiting Jupiter, and inside of Jupiter's giant magnetosphere, area of magnetic influence. And Jupiter's magnetic field is tilted. That little movie is showing that as Jupiter rotates around, the tilted magnetic field sort of flops and wobbles, and Europa is minding its own business orbiting around Jupiter, and it's feeling a changing magnetic field. And in response, Europa is generating its own little magnetic field that is swinging around to counteract Jupiter's. Well, that means Europa is behaving as a conductor, something that's essentially conducting electricity. And metal can do that, but the metal core is too far away. So we think what is conductive here in the shallow subsurface is a salty water ocean within Europa. So indirect, but very convincing evidence of an ocean beneath Europa. Not to scale. That's illustrating Europa orbiting Jupiter, just like Io does, in a somewhat eccentric orbit, getting farther and then closer to Jupiter. And as it gets closer, it gets stretched out, and as it's farther, it contracts back a bit. This happens every 85 hours. Every 3.55 Earth days, Europa is orbiting around Jupiter and getting stretched as much as 30 meters as it orbits around Jupiter in 85 hours. And so friction is going to mean that generates heat. And as we look at the other movie here, also not to scale, we can look at it from Europa's perspective. Europa is getting stretched out and actually nodding back and forth, librating as it orbits around Jupiter. So this tidal kneading of something like 30 meters every Europan day is generating heat in there. Enough heat to maintain a liquid water ocean beneath an ice shell something like 20 or 25-ish kilometers thick. We don't really know if the interior, if the mantle is hot or not. It depends on how squishy, how warm, how deformable the rock is. It's a little of a chicken and egg. If it starts out warm, it can stay warm. If it starts out cold, it might stay cold down there. We looked at those freckles earlier, the lenticulae. Those seem to be a sign that the ice shell of Europa, that 20-ish kilometer thick layer, is kind of oozing like a lava lamp. Okay, some in the room are old enough to remember lava lamps. Lava lamp?
Absolutely.
Of course you do. So now in a lava lamp, warm wax rises up through oil, and there's a light bulb down there. So there's no light bulb on Europa, but there's the tidal heat. That squeezing generates heat, and that heat is input mostly in the base of the ice shell there near the ocean, and that ice is warm enough that it can flow and rise buoyantly up toward the surface, and we think make these pits and spots and domes at the surface of Europa. This is a feature called a band, that red streak through the center. And when we use that sophisticated scientific tool known as Photoshop, we can cut out that band and put back together, reconstruct the surface on either side. And all those ridges match up. So you can see these ridges have been split. And there are some old bands that have been split. And so there was a fracture, and this thing pulled apart to make this band. And you can see somewhat of a parallel structure within it. Postdoc who's working with me at the Jet Propulsion Lab, Sam Howell, he studied mid-ocean ridges on the Earth's ocean floors, places where new rock is oozing upward to fill in gaps as the crustal plates are pulled apart, the oceanic plates. And so he said he wants to come and try to model the same thing for ice on Europa to explain these bands. And he put together this fantastic animation. Now the bottom of that model is where the ocean is. The top is the surface. It's really cold. It's 100 degrees Kelvin. Someday I'll remember the conversion. Really cold. So here the yellowish stuff is the colder near surface ice, and the bluish stuff is the warmer flowing ice. So it's a little counterintuitive. But near the base is where it's warm, near the top is where it's cold. And he runs his model for 1 million years. And when you see flowy things in this model, it's not liquid water, it's ice, because ice can flow over geologic timescales. And you'll see some white particles because it's entraining material from the ocean and bringing it up toward the surface. Boom. So he's pulling apart the model. There's convection going on, these blobs of warm ice rising up at the base and coming in and filling in that gap that's forming by the surface. So material from the ocean, we think, can actually get to the surface in these bands. So that'll be a really interesting place to check out with our spacecraft and maybe someday go with a lander. Then there are these chaos regions, and they're places where that icy surface has been broken up. It's as if something warm has come up from the interior and kind of cooked the surface. It's a little like a jigsaw puzzle with half the pieces gone here, where they've just broken apart. What we think is going on is there may be lakes within the ice shell, and if you melt ice, the volume's going to decrease when it goes from ice to water and cause the surface to collapse to make these chaos regions. And then that lake might freeze up and cause the surface to dome back up. So that's the current best model for how this forms, maybe related to, again, warm ice and that tidal heating going on beneath these chaos areas. Those will be fascinating places to look for subsurface water with the radar that our spacecraft is going to carry. Oh, scale, right, I didn't talk about scale. There's some familiar things. So LA would just about fit in there. There's probably less traffic on that commute.
I know, and there's a direct route from Griffith
The
to...
roads look just as smooth.
Yeah.
Got a little peak there. Griffith is on. We think Europa, like Enceladus at Saturn, may have plumes. Enceladus, we're sure. We can see them with the Cassini, or did see them with the Cassini spacecraft. Using the Hubble Space Telescope, there are hints of a glow of hydrogen and oxygen that have been seen on the limb of Europa several times during several Hubble orbits. So it may be that there are plumes at Europa as well, and there was a recent result that the Galileo spacecraft 20 years ago may have flown through a plume. There's a magnetic signature blip that now that we may understand what plumes look like at Europa, put that into the model, and voila, it well explains mysterious Galileo data from 20 years ago. So Europa may have the so-called ingredients for life. Liquid water, probably much more than all of Earth's oceans in the ice shell, in the ocean. Essential elements, elements from which organic molecules can be built, things like carbon, hydrogen, oxygen, phosphorus, sulfur. They're common, we expect them there, brought by impacts over the eons. Chemical energy is a tough one. Is there the energy in Europa's ocean that could support life? Thinking back to your high school chemistry, couldn't there be redox reactions in the ocean, reductants and oxidants? Well, oxidants can come from the surface. The surface is bathed in radiation, charged particles pouring down onto Europa's surface they're trapped in Jupiter's magnetosphere, and they rip apart H2O. The H floats away, the O stays behind. If that stuff can get into the ocean, it's a wonderful fuel for life, for microbial life. As far as the reductants, the other half of the reaction, chemical reactions between water and rock can create hydrogen-rich materials, reductants. Or, like in the Earth's black smokers, if the interior is hot and water seeps down there and cracks, it can come out charged in chemical nutrients. So Europa may have the chemical energy to permit simple life. And then is it a stable environment or is it a flash in the pan? Well, Europa's ocean has probably been there since the beginning of the solar system. So the Europa Clipper mission, we want to test these hypotheses. Some of these things we know better than others. They're the best we can do right now. We want to study Europa's ice shell and ocean, its composition, its geology, its activity. Are there plumes? And we also want to do reconnaissance for a future lander. Someday, we'll send a lander to Europa and be able to set down on some of this dark reddish stuff where maybe there are organic materials and dig down in there beneath the depth at which radiation processes the surface and scoop some of that stuff up and determine its composition in detail. But until then, we want to understand, does Europa have the ingredients for life, and are our models correct, or how do we need to change them? So that's what we're going to be doing with the Europa Clipper. There are two categories of instruments. There are 9 or 10, depending on how you want to count them because there are 2 cameras. So first there are the in situ instruments. Those are the instruments that measure in place from orbit their environment around them. There's a mass spectrometer that will sniff the very tenuous atmosphere at Europa, and if there are plumes, be able to sniff them and tell us the detailed composition. There's a dust analyzer. There's dust kicked off the surface. Europa's in this big cloud of dust. We can measure the composition of those particles knocked off of Europa. There's a magnetometer, IceMag, which will redo the Galileo spacecraft experiment of measuring that induced magnetic field, but in much more precise detail to get not just the existence of an ocean, but its thickness and even its salinity. A plasma instrument tells us the composition of the charged particles around Europa and is needed to understand that magnetic signature. There'll be the category of instruments circled in blue are remote sensing, so looking from afar at Europa. An ultraviolet spectrograph, so like Hubble, look in the ultraviolet to determine whether there's the glow of particles, charged particles interacting with gas that would indicate plumes. The ICE is the Europa imaging system. That's the 2 cameras. One is a wide-angle camera to map the surface, to get stereo imaging, give us topography that way, and color imaging. And there's a high-res camera that during close flybys, as close as 25 kilometers off the deck of Europa, will get images up to 0.5 meter per pixel. Yeah, it's going to be spectacular. And so we can also do nice mapping even from afar. We can look for plumes from afar. eThemis is our thermal instrument to look for hotspots, kind of like Cassini has done at Enceladus, to look for sites of activity. MISE is an infrared spectrometer, tell us the chemical fingerprints of what's on the surface, a great complement to SUDA and mass specs. And last but not at all least, REASON is our ice-penetrating radar that I alluded to before. Ice, cold ice at least, is very transparent at radar wavelengths. And so we'll shine radar at Europa, it'll travel through the ice, bounce off liquid water, and back to the spacecraft. So we'll be able to plumb the ice shell of Europa, find lakes, understand if those ridges have anything to do with water, and if Europa cooperates, we may be able to penetrate all the way down to the ocean and measure the ice shell thickness directly. So there's our little spacecraft, this model, and in this illustration.
How big is it really?
Well, from tip to tip, it's about the size of a basketball court.
Tip to tip of the panels?
Of the solar panels.
Okay.
That's right. So a person would be, maybe this big next to the Europa Clipper
LeBron
spacecraft.
James would be that big.
The high gain antenna, which is covered with a dome here, is 3 meters across. So I'll give you an idea of the scale. The magnetometer boom that sticks out the back there is 5 meters tall. The cameras and spectrometers, the remote sensing instruments, look downward as we fly by, while the mass spectrometer and the dust analyzer look forward. And the radar antennas are on the solar panels. So these long metal rods on the model here are the long wavelength radar, and the shorter wavelength radar hang off the solar arrays. So this is a big deal to put an instrument and integrate it right into the solar arrays. But we realized the electromagnetic influence of the solar arrays was a challenge for the radar, and let's take it head on and think of these as a system. And so the flyby configuration is shown up there. So you have to tilt this little model and move the solar panels to put them in that flyby configuration. The solar panels move together. So when we're not doing a flyby, we're tracking the sun to power the spacecraft and charge up the battery, and then we go in for the flyby and gather lots of data all at once and zoom on out. So we're in orbit around Jupiter. The sum of the orbits is shown there. And we're flying by Europa something like 45 times. The colors there are showing the buildup of radiation as the orbit goes on to our maximum of 3 megarads there in red.
Where's the spacecraft being built?
It's being built at JPL.
Yep. Is it going to be launched by a Delta?
As far as launch, it could be a conventional rocket, a Delta IV Heavy, or a Falcon Heavy, or it could go on the new SLS, Space Launch System. And if we go on a conventional rocket, a Delta IV Heavy or a Falcon Heavy, it'll take almost 8 years to get there because we have to do the celestial billiards by the inner solar system to get gravitational slingshot out. However, on the SLS, we can go direct, 3-year travel time. Okay? So one of those is past my retirement and the other isn't. So you know what
Forget it, you're not
what I would
retiring.
favor.
That's not happening. You can't. You have to.
This illustration is showing those
Sorry, Mabel.
flyby. This illustration is showing those flyby trajectories. And this is schematic. This is our current tour. It's going to change over time because we're working to optimize. And you can see as we do these flybys at different latitudes and try to cover all of the surface as best we can. Now we can't quite cover the leading and trailing hemispheres as well because then we'd be flying right into Europa, which we don't want to do. And planetary protection will not allow us to do that. We have to guarantee that that's not going to happen.
Is that why we
I love
cannot
Jupiter going
orbit
by. Planetary protection is not the reason we can't orbit Europa. We were originally looking at a Europa orbiter concept, but then we're bathed in the radiation all the time we're there. This way, we dip into the radiation and we get out, right, and transfer the data back.
Like Juno.
Yes, analogous to Juno. Juno has the advantage that they're out of the plane, whereas we stay in the plane, so it's even worse in the plasma sheet. On the right are shown coverage maps from the various remote sensing instruments, the radar tracks in the top one, and then the various other remote sensing instruments. So those are the kinds of details we're working.
Would the ice shell protect anything that might be in the subsurface ocean from radiation?
The ice shell, all you need is about a meter of ice to stop all the radiation. So even 10 centimeters of ice stops most of the radiation. Over time, some will penetrate deeper, the more energetic particles.
Is radiation the primary limiting factor in the length of the mission?
Radiation is a limiting factor in the length of the mission, as is the lifetime of the solar rays. The solar rays will degrade over time because of radiation. And so power will become more and more of a problem as the mission goes on. So we're planning to make sure we have enough power at end of mission. That's how we plan these things. That means at the beginning we can transmit lots of data, do lots
And how
of cool
will you
things.
scuttle it? At the spacecraft when it's done for planetary protection?
Oh, at the end of the mission.
Yeah.
The current plan is send it into Jupiter.
To Jupiter.
Like Galileo was. Carl Sagan says it's okay, and the planetary protection officer says it's okay. Though there has been discussion of whether it's okay to crash into Ganymede and Callisto because there's not going to be, we're not contaminating any environment where we could someday go to search for life. That's not going to be the case at the surfaces of Ganymede and Callisto anyway. Europa, we cannot go near, and we have to show that we're not going to contaminate Europa's ocean with any microbes. So let me finish with this very cool animation of the spacecraft flying by Europa. This is just a still shot from what you'll see of the various instruments as they're looking down and doing their things, and as the spacecraft's turning and the solar rays are moving around. Let's see if this will. So it's just transmitted. Whoops. Was that me?
No,
it's
that's-
data to Earth. It's doing an ultraviolet scan of Europa as we put the nadir deck, as we call it, facing Europa, looking for plumes and analyzing the atmosphere. Which instrument is on is being shown on the bottom left and also at the top. The magnetometer and the plasma instrument are on all the time. There was a little thermal calibration. The panel's turning there and putting us into the nearly the flyby configuration. We'll see the panels rotate when we're actually in the flyby configuration. Some of the instruments don't scan themselves, so we do a scan with the spacecraft when we're far out there for the ultraviolet and the thermal instrument and to get a global color image. You can see the flashes of the high-res camera, the thermal instruments staying on, and the ultraviolet image spectrograph staying on, wide-angle camera pictures of Europa flashing by. Now we rotate to put the radar antennas into the standard close approach position as we turn on all the instruments at once and zoom by Europa. And that's way sped up, of course. On the way out, we rinse and repeat. We kind of do it backwards. And then get ready to transmit all that data back to Earth. It's actually turned out to be a challenge for the avionics, the electronics, to get all that data that's being generated through and into the computer memory that quickly. There's the joint scan again. We try to keep the operations as simple as possible, and that's why we want all the instruments to be able to observe at once and to do a similar thing on each flyby, though tailored somewhat for each flyby. And also taking the data all together means, well, scientists don't argue about whose turn it is, and because then we get the best science by being able to observe the same things with the suite of instruments and think of them as complementary and getting us all that information that we can take back and analyze and make available to the science community and to the public. So that's a snapshot of where we are with the Europa Clipper.
So before we take questions from the audience, I just want to know a little bit about the status of the mission and also a little bit about the history. Like, when did it begin? When did you start working on this mission? We always like to see how lives are shaped around them.
It's been a while.
And then also just in the arc, you know, are you locked with your spacecraft? Do you still have time for changes?
Right.
You know, what's the calendar? What's the timeline? What are the milestones that we should be looking for?
We just went through what's called the preliminary design review, and we're waiting for the formal report from the board, which goes to us and goes to NASA and says how we did. Overall, the report out from the board was very positive, and this is the time where NASA says, "Yep, okay, ready to go start building." Right. So that's this big review. And there'll be some confirmations and the like and reviews that happen between now and the spring to give us the go-ahead. The mission started, boy, it's been such a blur because we're rushing toward launch, right? The earliest launch would be in summer of 22, and every day we're working hard to get there. I got involved in my first Europa science definition team in 1998. And I moved to JPL in 2006 because it was clear that to get a flagship mission going, they needed someone to really push it forward. I was at University of Colorado at the time as a professor and essentially got an offer to come to JPL and help get this mission going. I said, okay, I'll go to JPL for 3 years. If it doesn't get going, I'm going to go back to academia. We got the go-ahead from NASA to start the mission 9 years after that in 2015. And so we're on our way. Exploring the outer solar system is not for the faint of heart. It really takes dedication. And you can't just think about, you know, oh, are we there yet, right? It has to be about the journey. And it has to be about enjoying what you're doing along the way and building a team of people that you want to be working with until 2030 or so. And we've got a fantastic science team and a great engineering team. And looking forward to all these years together and then finally getting there.
So are there questions from the audience? Yes.
And when the difference between the launch vehicles you mentioned, does that affect the spacecraft or your design at all, or were the same thing on either type of?
The fact that we've been working to ensure that we're compatible with any of those launch vehicles. And so we've made the spacecraft so that no matter which of those launch vehicles we're on, we'll be okay. And the limiting case is the SLS Direct in terms of the mass. There's a little configuration issue because the Falcon Heavy would we'd be testing sideways, and then they'd lift us up. That's the level of detail we're looking at it, and relatively trivial. But yes, we're making sure we're compatible.
Does it have a electric or chemical propulsion system on board, or can we discuss propulsion?
Oh, yeah, well, we have our thrusters on board in terms of the hydrazine propulsion to maneuver the spacecraft, if that's what you mean. So, so yeah, we have. I'd have to go back to the diagram, but that's okay. We have many thrusters and engines along the bottom of the spacecraft. Let me, if I can point them out here on the bottom of this illustration.
Okay, yes.
Yeah, I was wondering about the color of the moon, the reddish kind of color and the white. Does that have anything to do with the iron core and the salt?
The ruddy color of Europa, really this color is exaggerated when you see these images. It's probably a pale ochre in reality. And we think it's probably related to sulfur contaminants, or it might be from radiation darkening of sodium chloride. Regular table salt might be a component of Europa's surface, and that browns from radiation. So those are kind of the end-member models, sulfur compounds and or sodium chloride that are brownish in the radiation environment.
Just curious, the image that we're going to see when it's circling, will it be comparable distance-wise to what we saw of the image of Pluto?
Will be much closer to Europa than New Horizons was to Pluto.
We'll see more detail.
We'll see a lot more detail. The New Horizons images were, I think, on the order 60, 70-ish.
I just remember the
meters per
size
pixel.
of the lake in Central Park. That's what Alan told us when he was here. So you could see the lake in Central
And we'll get up to half meter per pixel. So think more in terms of high-rise, the high-rise imager at Mars, in terms of the level of detail for some of those closest images.
Yes. Yeah.
How does it happen that some objects in the solar system get a lot of water and some don't?
Out in the outer solar system, when the planets formed, there was lots of H2O, right? And the H2O in the inner solar system, right, didn't condense, it was just too warm. And out at Jupiter, near Jupiter, it was probably too warm for a lot of H2O to condense. And then farther out from Jupiter, out by Ganymede and Callisto, a lot more H2O condensed out. So Jupiter's system is kind of like a mini solar system in terms of the temperature through it when those moons were forming. And out at Callisto, you even get a lot of CO2 ice, which condensed out there. And then if you go farther out in the solar system, like at Pluto, you start getting things like nitrogen ice and methane ice, things that condense at much, much lower temperatures.
Yeah. No, you go ahead.
The sulfur you referred to, did that come from Io?
One idea is that some of the sulfur comes from Io, so some amount of it probably does. But the dark reddish stuff correlates to where the surface has been breached in some way, where we see big impact structures that penetrated deeply, or where those bands are, right? So if stuff's coming from Io, it wouldn't preferentially land on the places where material has been exposed. So there's probably some from Io, but it's probably coming from Europa's ocean, from its interior.
When will the first and last flybys be?
When are the first and last flybys going to be? So, if we launch in 22, and if we're on the SLS, then we're late 25 arrival, and then I think that puts us to the first Europa flyby sometime in 26. I don't know exactly. But then it's about 2.5 years of making flybys of Europa, about every 14 days, when we're really swooping by. It takes the first few or big looping orbits. And then there are some where we don't where we fly by Ganymede and Callisto while we're changing over, because we're going to do the anti-Jovian hemisphere first, the hemisphere of Europa facing away from Jupiter, and then change the orbit and do the hemisphere that faces Jupiter. And I don't have the dates memorized because we're sure it's going to change, because the tour will evolve over time.
Yes, up there all the way in the back.
You were talking about some of the different kinds of ice that's out there in the solar system, like carbon dioxide ice and methane ice. How do we know that Europa is just water ice?
So how do we know Europa is just water ice and not these other more exotic ices? The Galileo spacecraft flew by Europa about a dozen times from '96 to the last one must have been in 2002-ish. And it had an infrared spectrometer to tell us about the spectral fingerprints of the surface. Plus, from Earth-based observations, we knew of water ice there. From the Galileo spacecraft, being closer and getting higher resolution, the Galileo scientists found some evidence of a little bit of CO2 ice on Europa. So there may be other more exotic ices, but you wouldn't expect things like ammonia or methane. Is probably just too warm in the Jupiter system for those.
All right. Yes, Larry?
Why Europa versus some other targets, say Titan or Enceladus or multiple targets?
So why Europa instead of other icy moons? I want to explore them all, right? We're going to get there. We've got to start somewhere. And Europa has probably the greatest potential for life in our solar system. And you can get into debates with the Enceladus folks a little bit. Enceladus is an exciting place too. The question is whether Enceladus has gone through a burst of activity, or is it recent activity? Has there been enough time for Enceladus's ocean to simmer and life to form? But also this mission got going, or at least the concept and the studies got going, and we're way ahead of Enceladus and Titan because Cassini came along later, and so we and only recently finished. So it took longer to really understand those moons and understand the best ways to explore those moons. So they're next in the outer solar system queue.
All right, I have time for one more question. I feel like I've shortchanged this side of the house. Is there? Oh, they're all frozen now. All right, we'll take the hand in the very back.
Was there any consideration for a probe to drop down on the moon?
We did consider options for probes, landers. Was there something that this mission, the Europa Clipper, could carry? To get to the surface is challenging. So Titan, big atmosphere. It's actually relatively easy to put a probe down on the surface. It's tough at Europa, where there's essentially no atmosphere to help with braking, and so you need propulsion. So you have to carry all that propulsion with you to slow down a probe and have it land safely. So we did look into that in detail, and to get even really a small package onto the surface would essentially double the mass of the Clipper spacecraft to get something like, I forget what it was, somewhere between 5 and 20 kilograms down onto the surface.
Then I'd imagine the planetary protection people wouldn't be pleased.
I have been wondering about that with regard to Titan, as a matter of fact.
Well, Titan we're not as worried about in terms of planetary protection, the cold surface environment. And an Earth organism probably wouldn't multiply in an ethane-methane lake. But in terms of a lander, we have to very carefully think about planetary protection for a lander, where one idea is you carry an explosive and you blow the thing up at the end so that the radiation environment sterilizes even the innards of the spacecraft.
Or causes mutations and then
Nothing's going to live at the surface. The issue
Call
is
Stanley first.
The issue is you don't want to bury organisms and then they're in a chaos area and scooped into the interior.
Yeah. Well, I know there are other questions, but we are out of time, and so let's thank Bob for coming by and telling us all about it.